Hello. In this lecture, we want to talk about the relationship between data visualization and machine learning. The two fields of data visualization and machine learning have come close to each other in recent years more than ever before. We are going to discuss the interplay of data visualization and machine learning. We will specifically explain the role of machine learning in data visualization and the role of data visualization in machine learning. We will then go over several examples where data visualization plays a significant role in developing a machine learning model. We visualize our data to make sense of it. Also, we develop machine learning algorithms to make sense of our data. Therefore, machine learning and visualization techniques can help each other out, and in fact, they can complement each other. Machine learning can support and help visualization of data. Machine learning techniques such as dimensionality reduction, clustering, and classification have been used on a regular basis to transform complex and high-dimensional data into representations well suited for visualization and visual exploration. Also, machine learning identifies prominent patterns to highlight in visualization. At the same time, data visualization plays a fundamental role in machine learning. In almost every step of machine learning, visualization comes into play. In the data pre-processing step, we use data visualizations to detect outliers, to determine the degree of class imbalance in our dataset, to identify missing data, so on and so forth. When we want to explore the data, visualization enables us to identify linear or nonlinear relationships between features in the dataset and also to identify trends and patterns in the data. Model tuning and evaluation. One of the primary difficulties in any machine learning approach is to make the model generalized so that it can perform well with the new data and not just the data it has already been trained on. In order to achieve this, we need to adjust different parameters of our machine learning model, such as proper number of clusters in k-means clustering, proper number of trees in random forest classification, optimal number of epochs in deep learning, and many other examples of these parameters. Also, we can evaluate the model by visualizing its performance to ensure that we are not overfitting or underfitting the data. In case of clustering, visualization helps us evaluate the clusters. When we are ready to present our findings, once again visualization comes into play. We create suitable visualizations customized for our target audience, showing the important part of our machine learning results. Now, let's elaborate more on these. Outlier detection is a pre-processing technique that permits the identification of strange data points in a dataset. For example, it could be a data point that has been incorrectly entered or measured. Usually, removing outliers leads to better fits and more accurate predictions, as you can see in these two scatter plots. Outlier detection is only one part of data pre-processing. Data pre-processing also includes finding missing values, standardization, normalization, formatting, dropping duplicates, identification of class imbalance, so on and so forth. Identifying data distributions and correlations in data can reveal patterns and points of interest. Correlation is one of the most widely used measures in machine learning and statistics. The correlation coefficient summarizes the association or a statistical relationship between two variables. Several types of correlation coefficient exist, but they all assume values in the range from -1 to +1, where plus and -1 indicate the strongest possible agreement and 0 means the strongest possible disagreement. The Pearson correlation coefficient, or R, is a measure of the strength and direction of the linear relationship between two variables. Pearson correlation coefficient is the best known and most commonly used type of correlation coefficient, and whenever we just say correlation, we mean Pearson correlation. Here I'm showing many scatterplot visualizations. They all make sense, and the reason, for example, for this scatterplot, the correlation coefficient is 0 is because we measured linear relationship, and the relationship that we see here is nonlinear. Again, these visualizations can reveal patterns and points of interest, so they have the potential to be very useful in the preliminary steps of a machine learning project. In this video, we are playing with a dataset to show you how the correlation coefficient can change and how we can go from perfect negative correlation to perfect positive correlation. It goes without saying that in this example, we are looking at linear correlation, and the type of it is Pearson correlation. Clustering data into meaningful groups has always been an important task in data analysis and knowledge discovery. Clustering is an unsupervised machine learning approach where the results of the approach depend on the algorithm used. Visualization is the first step in cluster analysis. Consider the following two scenarios. Visualization of data significantly helps us with parameter selection. For example, K in K-means clustering and epsilon in dbSCAN clustering. In case of K-means clustering, which is one of the most popular clustering algorithms, choosing the correct value for K or number of clusters is important. Data visualization makes this selection process easier. Similarly, visualization helps us choose the optimal epsilon in dbSCAN, which is a density-based spatial clustering technique. Scenario number 2, visualization of data is also required when we want to evaluate the quality of the detected clusters. For example, we need to see the clusters produced by K-means clustering to evaluate them. There are a number of metrics used to quantify the quality of clustering, but we need to see the clusters first to ensure that we choose the right metric. In this example, we see that K-means clustering has detected low quality clusters. This is what we wanted to achieve, and this is what we got from K-means clustering. But we can see that EM clustering or expectation maximization clustering achieve near perfect results. Sometimes the data that we deal with is geospatial data, and in that case, visualization is a must. Given the nature of geospatial data, visualizing it on maps can be greatly insightful. Geospatial data refers to any data that includes a set of attributes of some geographic locations. Pretty much any data that contains geographical information within it is considered geospatial data. Different clustering algorithms can be applied to geospatial data. Data points within a cluster show a high degree of similarity, whereas the clusters are as much dissimilar as possible. The goal of clustering is to do a generalization and to reveal a relationship between spatial and non-spatial attributes. Here is an example in which, with the help of K-means clustering, we created spatial clusters of a company's customers to improve logistics. By visualizing these clusters on this map, we will be able to evaluate them and plan accordingly. And here is another example where geospatial data contains the weather condition attributes in Australian cities. Both the geospatial data and the detected clusters in each iteration of K-means are presented on this map. Again, we need to visualize these clusters on proper maps in order to evaluate them. Okay, we went over model tuning and evaluation for clustering methods. Now, let's switch to classification methods, which are another group of machine learning algorithms, and see how visualization comes handy for their model tuning and evaluation. For all types of classifiers, keeping track of hyperparameters and corresponding evaluation metrics is important, because small changes in hyperparameters can sometimes have a big impact on the quality of the model. For example, for a random forest classifier model, the number of trees is an important parameter, which is the number of single decision trees included in the model, and it represents the model's complexity. Increasing the number of trees beyond a certain number is unnecessary, and it does not lead to significant performance gains. So it would only increase the computational cost, since the training time is going to be longer when we have a higher number of trees. Accordingly, it is essential to visualize a performance metric such as the validation error of the model for a growing number of trees in order to choose the optimal value of this parameter. In deep learning classification, one epoch is when an entire data set is passed forward and backward through the neural network only once. So each sample in the training data set has had an opportunity to update the internal model parameters. Using one epoch leads to underfitting of the model's curve. As the number of epochs increases, more number of times the weights are changed in the neural network, and the curve representing loss goes from underfitting to optimal and to overfitting. Visualizing the training loss and validation loss over a number of epochs is a good way to determine if the model has been sufficiently trained. This is important, and it ensures that the deep learning model is not undertrained, and at the same time it is not overtrained. For the SVM classification algorithm, visualization of the data in the training stage can provide guidance in choosing proper values for input parameters. In SVM classification, the width of the gap between the two categories is determined by a parameter called epsilon. So, the value of epsilon affects the number of support vectors used to construct the decision boundary. Here we have the results of two SVM regression models after training on some random linear data. This one has a large gap between the two categories, and the gap on this one is smaller. So we have a smaller value for epsilon. The larger the epsilon, the larger the errors that we tolerate in our solution, which means the model is underfitting the training data. In contrast, if epsilon becomes very small, every error is penalized, so we end up with many support vectors, which is a sign of overfitting. With the help of these visualizations, we can tune epsilon to gain the desired accuracy from our SVM model. Data visualization is essential in every step of machine learning. Once training is complete, it's time to shed light on the performance of the model or models to see if they are any good. And this step is called model evaluation. One of the most commonly used visualizations to evaluate the performance of machine learning algorithms is the receiver operating characteristic or ROC curve, which visualizes how well models can classify a binary outcome. ROC curve is generated by plotting the true positive rate of a model against its false positive rate for each possible cutoff value for distinguishing the two values of a binary outcome. These ROC curves help us understand our models better and pick the best model, which is this model in this example. For example, we may find that an SVM classifier performs better than a decision tree classifier, and we pick that. And this is a stacked bar chart that visualizes individual performance metrics for multiple classifiers. We can compare them and choose the classifier that meets our needs. These were just two examples. In fact, we can have a variety of visualizations to evaluate the performance of our machine learning models. We should create visualizations of various experiments in order to optimize our classifier's parameters. We can do this ourselves using Python, R, or other programming languages, or we can take advantage of tools and libraries that enable us to easily visualize and explore various parameter-metric interactions. Here I'm showing the names of some of these tools and libraries. Some of them have so many other capabilities, and some are just specialized in machine learning experiment tracking and visualization. So, our model is finally done running. We evaluated it and optimized all of the parameters we could to obtain the best results, and we are ready to present our findings. Now what? It's no secret that the field of machine learning is considered heavy on theory. It has math, statistics, and computer science, all of them. While machine learning practitioners tend to enjoy the depth and the underlying theories, colleagues and clients outside the bubble find it difficult to participate in the conversation. Therefore, simplicity is key in making impactful visualizations. For example, this visualization represents a summary of K-means clustering of customers of a company based on their loyalty. Accordingly, we can develop an engagement strategy for each of these customer clusters. For classification models, accuracy, precision, recall, ROC curves, and confusion matrices are great at representing the performance of our models. All of these metrics can be visualized in a simple fashion in order to effectively communicate the results of machine learning. For example, this confusion matrix shows a summary of COVID-19 prediction results from classification of chest X-ray images. Audience can easily see that our model can strongly predict the COVID negative class. Also, we can see that sometimes our model misses some of the COVID positive cases. Notice how much the color coding in this visualization and the guide that we placed next to it can be helpful for a non-technical audience. We also need to adjust our language and terminology to our target audience. Let's say our model has a low recall, producing a lot of false negatives. During a team meeting, we need to communicate our progress and plans for next steps. The recall word doesn't really mean anything to our non-technical colleagues, so perhaps we should not use it, and instead we say our model misses some COVID positive patients and fails to identify them. Our next step might be to adjust some parts of the model so that the miss rate is reduced. To summarize this lecture, there is a strong interplay between machine learning and data visualization. Machine learning facilitates complex and high-dimensional visualizations and identifies prominent patterns to highlight in such visualizations. And data visualization supports machine learning. In almost every step of a machine learning project, visualization comes into play and has a significant role. So, we can say that the fields of machine learning and data visualization are tightly interwoven together. We showed quite a few examples of the interplay between machine learning and data visualization. Of course, there are tons of more examples to show how these two fields are strongly connected. Okay, I will see you soon. Take care.